Hello, y'all. Welcome to lesson 103 of my DP chemistry curriculum. Today we're going over reactivity 3.1.13. This is an HL topic. We're going to talk about how pH curves of different combinations of strong and weak monoprotic acids and bases have characteristic shapes and features. So we should be able to interpret the general shapes of pH curves for all four combinations of strong and weak acids and bases. And as we do that, we'll start exploring some similarities between them. So what we're going to start out with is just a little bit about the pH curve when we're dealing with a weak acid and strong base. To do this, we're actually going to start with a simple comparison between a strong and a strong. So I'm going to go ahead and just make my curve right here. We have our pH on the y-axis with our neutral point at 7, our high point at 14, and low point at 0, with our volume added. So for this, we'll assume that we're adding base into a acid, into a strong acid. So this is going to be a strong acid, strong base. And I'll just usually put the second one as the titrant and the first one as the analyte. When we look at this curve, we already seen this one before, but it's got some characteristic features. First off, we know that our equivalence point is right at 7. And that is due to the neutrality of the salt. So we explored that when we looked at the previous lesson, which was pH of salt solutions, as well as looking at pH curves previously. So that's going to be right at 7. Our starting pH is approximately somewhere around 1, and we're ending somewhere around 13 for our pH. So that's our strong acid, strong base. See if I can copy this without getting any of my other stuff. So when we look at now something like our weak acid, and we are titrating in our strong base, well, we're actually going to start with a higher pH because our weak acid's starting pH will usually be somewhere a little more towards a neutral, like let's say, for example, maybe around 3. Furthermore, it's not so flat. It's going to actually rise up a little. That might be a little too steep. Rise up. And then we hit our inflection point. And then the top half is going to resemble the same as the top half of our strong base. These are pretty equivalent. The first part, though, is a little different. For one, we're starting higher with our weak acid. So we'll start taking note of what's different. So we start at a higher pH because our pH of our weak acid is less acidic than that of our base. Furthermore, we have an increase as strong base is added. That's relatively constant. In addition to that, if we look at our equivalence point, which I'll start just referencing as EP, we'll notice it's actually a bit higher. It's going to be greater than 7. And we learn that because our salt of our weak acid actually is a conjugate base. So even when our solution is perfectly neutralized, the actual remaining salt is slightly basic. So our new point is that our equivalence point is greater than 7 for our pH. Lastly, or not lastly, we have a couple other points. We actually create a buffer region. Create a buffer region. That buffer region is actually also this relatively constant pH section. Now, we are going to learn more about buffers in another video. So that is the buffer region. So right now I'm just going to lightly touch on what the buffer region is. But at the buffer region, what we're really looking at is a solution that contains both our weak acid HA and our A minus, which is going to be our conjugate base. So this region has both our acid and our conjugate base. And because of this, the buffer region can resist changes to pH. And it very well does. It can keep a relatively stable pH within a certain region. So in addition to this, we also now have a new point. We create what's called the half equivalence point. The half equivalence point is half the volume of titrant added to reach the actual true equivalence point. I'm going to pause this and readjust my graph just a little bit. So for our half equivalence point, it'll be right in the middle of that buffer region. So this is our half EQ, or EP. So that half equivalence point is where half the volume of titrant is used up, or to reach the equivalent point. Now, this half equivalence point is a very significant value. This is where exactly half of the weak acid, or in our case HA, is neutralized. Now, the reason this is important is because for a weak acid, when we neutralize half of it, based on the low Ka values of a weak acid, what that actually ends up meaning is that the concentration of our acid is pretty equivalent to the concentration of our conjugate base. So we can calculate our conjugate base from that, as well as the hydronium concentration, which has been neutralized. So this is what we actually call an ideal buffer as well. So the property of the buffer region is most perfect at the half equivalence point. Lastly, at half equivalence point, we can determine the pKa because the pH is equal to pKa. And therefore, because pH is equal to the pKa, we can also tell that the concentration of hydrogen ions is equal to, the Ka. So these can all be determined at the half equivalence point. So I'll go back up to our graph, and this is the pKa value as well as the pH value. So that is what it means to be at half equivalence point, and this is what we expect in a pH curve for a weak acid and strong base. What we're going to move on to now is we're going to do the pH curve for a weak base and strong acid. So I'll start out by putting my same graph. And now that we're starting with a weak base, we're actually going to start higher. Now, again, we're not going to start at the height of something such as a strong base like sodium hydroxide or potassium hydroxide. This might be something like sodium hydrogen carbonate or ammonia. We are once again going to create a buffer region. Then we are going to shoot down and get that strong acid section. So this is going to be our weak base titrated with a strong acid. So I'm going to go ahead and change that to volume of strong acid. You'll notice quite a few similarities here. First off, if we look at our equivalence point, you'll notice that this is less than 7. So we can write down that the equivalence point is less than 7. And once again, that's because the conjugate acid of the weak base is now creating a acidic salt, or it is an acidic salt. And so furthermore, at half equivalence point, so we'll go ahead and notate that, the pH, once again, of the conjugate acid of the weak base is equal to pKa. So once again, we have pH still equals pKa. Now, because we're talking about a base, we can also actually say the pOH is equal to the pKb at the same point. So either way works. With these curves, the big thing for the DP exam, so these are the big things of note, students should be able to find for any combination of strong acid, strong base, weak acid, or weak base, or pH curves. So from any of the combinations or just the pH curves, you need to be able to identify where the oops, intercept of the pH curve, or sorry, pH axis, the curve starts. So intercept of the pH axis wherever the curve starts. So if it's a weak base, you should know it starts somewhere in like the 11 range. If it's a weak acid, somewhere in the 3, 4 range. Strong base, somewhere in the 13, 14. Strong acid, somewhere in the 0, 1. So you need to be able to indicate where the curve starts. And I'll write that a little more. Furthermore, you should be able to identify the equivalence point. So you need to be able to find that inflection point on the pH curve. If it exists, you need to be able to identify the buffer region. And finally, number 4, you need to be able to identify where pH equals pKa or pOH equals pKb, which is also the half equivalence point. Now, the half equivalence point, once again, only happens in a buffer region. So you need to have that previous point on this list. Now, the last thing in this whole pH curve business is what if we have a weak base with a weak acid? We'll go ahead and change that over to weak acid added. Now, because this is a weak base starting point, we know our pH is going to start a little lower. We're going to have that kind of buffer region, some inflection, and then drop off. This is a pretty uneventful pH curve. Now, because they're both weak, and as we mentioned before, a weak acid and a weak base generally produce a pretty neutral salt, meaning that our equivalence point is usually going to be around 7. And the key aspects here are we start slightly alkaline, slightly alkaline, and we end slightly acidic. And our equivalence point is approximately 7 or relatively neutral. This is about it for strong acid, strong base, weak base type pH curves. You should be able to identify all these points and be able to describe them or explain what's going on in further detail on your DP exam. We are going to cover buffer regions in about 2 more lessons and what buffers are and how they work. But otherwise, I hope this helps and have a great day.